Hi folks, and welcome back to Physics with Captain Rod. I'm making this video here to help you learn how to draw good free body diagrams and use torque equations to solve problems. So what we're looking at is some person, for some reason, I don't know why, has hung this 40 kilogram lamb from a rope, which is tied off here to this beam, which is, some stuff is written about it up here, 4 meters long and 20 kilograms. And then this beam is attached to this pin here, which is free to rotate. And what we're going to do, I wrote this up over here. We're going to look for the two tensions. That's referring to this rope and this rope. And this F sub P means the force applied from the pin onto the beam. That's occurring right there. So why would somebody do this? You might say, you know, I don't know. I mean, there are people who have shot sports cars at Mars. So who knows? But just humor me with this example, and we'll get through it. So this problem really is about the beam, and what we're going to do is a free body of the beam. Now, when we draw a free body, right, I'm going to cheat and do this. Whether we include the lamb or not is kind of our choice. I'm going to go ahead and include it, as part of our system. And I'm going to cheat here because this thing will do a copy paste very easily. All right, so this is going to be our system. Now, the difference, you know, like whether that lamb is included or not, has to do with basically just, is the lamb in the picture? Since the answer is yes, all right, when we get to our free body now, we're going to put a gravitational force down for the lamb right here, M sub G here, and that is the mass of the lamb. Now, had we not included the lamb, we would be putting a tension down on the beam, which is equal to the weight of the lamb, and you'd get that from a free body of just the lamb. That would, you know, a free body of just the lamb, hopefully reasonably simply shows that the upward tension in the rope minus the mg for the lamb are equal. So the tension in that rope is going to equal the weight of that lamb. If we include the lamb in the free body, then our force is the mg for the lamb, and the tension in the rope there is internal. If we don't include the lamb in the free body, we have a downward tension equal to the weight of the lamb. Either way, we have a force vector down here equal to that value. Now, other forces acting on the beam. So the beam has got a gravitational force acting down at its geometric center. So we've got an mg, and this is for the beam. Now right here, surface in contact, right? So we got a tension acting to the right. Go ahead and call that, how about tension 2? Now effectively, we've already found tension 1. That's the weight of the lamb, roughly 500 newtons, mg. Now we're going to look for the tension in this rope and the force at the pin. Now that pin force is one that a lot of people miss. Let me get rid of this here. Really, you know, if there was nothing going on right here and you look at the free body, this beam would be accelerating down and to the right. There's got to be a pin or something applying a force to that beam. Now the force direction is not clear. There is no reason to believe that the force is parallel to the beam. There's no reason to believe this in any way, shape, or form. So I'm going to actually, you know, maybe put it at some sort of angle. Boom. So unknown force at an unknown angle. So there is a complete free body of the beam. Now, that unknown pin force that has an unknown P and an unknown theta, usually what we end up doing is breaking those into components. So it's quite common, if you're going to do that anyway, to just draw the free body already in component form. So rather than a force P, what I'm going to do is put a single force for the X component, call that one PX, and another one for the Y component. It's still two unknowns. Before it was an unknown force P and an unknown theta. Now we have an unknown PX and a PY. So it's not like we've traded for two unknowns anyway. Now my force vectors really are not, I've not really scaled them correctly. if I were to scale them correctly, just some things to consider. The lamb, this vector should be roughly twice this one because of the masses. These two added together should have the same length as this one. Oops. And these two should be the same length. But getting those actually perfect in this picture, in this context, it really is not that important. It won't make a difference in our analysis. All right, now, because I need a little room here, I'll shrink that free body down a little bit, draw it a little higher. So the very first part of these problems is getting a good free body diagram, right? And remember, put gravitational forces in, and then you're looking for contact points, all right? The beam is in, well, if we didn't include the lamb, we've got a contact here, a tension, another contact here, and then the pin. So there are 3 contact forces on that beam. If we include the lamb as part of the system, then we have 2 mg's, one for the lamb, one for the beam, and then 2 contacts here and here. In any case, though, you really need to have all of the force vectors shown. All right, the next step now, right, after we get the free body done, is to start writing force equations, or I'm sorry, equations, right? We can start with force equations, but torque has this nice property that any force that goes through the point you pick doesn't produce any torque about that point. So I'm going to point out that this point right here, the red dot here where the pin is, both px and py go through that point. So any torque equations that we do not, or that we write about that point, will not have px or py show up. Now, I forgot to label this angle theta here as far as its numerical value. I'm just going to put theta because I actually am not going to finish this problem right down to a number. The point of this problem is just how to do the free body and then write the equations. Right? So it doesn't really matter what that angle is. In this picture, this is theta. So what we're going to do now is we're going to write a torque equation. Sum of all torques equals 0. And I'm even just going to color code the sum of all torques about the red dot here. And I usually just stick to counterclockwise positive with these torque equations. So summing torques about this point, px, py, do not show up. The first torque term that I'm going to put in there is 1 for the weight of the beam, the mg. Now the force is mg, and again that m is mass of the beam. Now we got to get the right distance. This force vector have what's called a line of action, which is all along this line. The distance that you use has to make a right angle to the line of action. I'm going to put that distance in green. That is this distance, whoops, green I said. That is this distance right here. That distance, right, from this triangle, this right triangle, the hypotenuse, by the way, would be half the length. So that green distance is equal to L over 2 times, whoops, not sine, cosine theta, where theta is some angle, presumably given in whatever problem you're working on. This torque term is positive because this force makes this beam want to rotate counterclockwise about that point. Okay, next term, tension 2. Now the line of action for tension 2 looks like this. The distance we need, I'll draw this one in green, is this, whoops, keep missing my green there, is this distance, because the distance needs to make a right angle to the line of action. That distance is the same as this right here, opposite theta, so that distance is L over 2 sine theta. So our torque term is going to be tension 2 times L over 2 sine theta, and that torque term is negative because this force is making the beam want to rotate clockwise about the red dot. All right, next force, the mg. All right, for the lamb, the mg acts all along this line. The distance we need, again I'll do this in green, is from here to here. It's got to make a right angle to the line of action. And from this right triangle, that distance is L cosine theta. So we're going to have mg, and that mass is mass of the lamb, times L sine theta. And that torque term is positive because this force vector makes this beam want to rotate counterclockwise about that point. And that's it. So, equals 0. Now, I don't have a calculator on me. I'm going to let the viewers finish this up here. You know, measure this angle if you have to. That looks like about 65 degrees, give or take. You know, you're putting numbers in here, here, here. The length of this will divide out. That length is in every term. Put numbers here, here, here. You can solve this for tension 2. And that's now a known value. Next, we can write a force equation. Maybe sum of all forces in the x direction equals 0. It doesn't matter if we do left or right positive. I'm going to do left positive because I'm bored, or just feel like, you know, being a non-conformer here. So, and again, we look at our free body. There are only 2 forces in the x direction, this one and this one. Now, had we done right positive, right, that would be like this. Doesn't really matter though, either way we're going to get the same solution. You're going to get that Px is equal to tension 2. And then we can get Py from a force equation in the y direction. And that equation, and again, you get these from your free body. You're looking here. Right, Py is up. Px does not have a y component, neither does tension 2. Minus mg for the beam, minus mg for the lamb, and that's it, equals 0. And from here you could get Py. So we would now have this force vector. We would have it in component form, Px to the left, Py up. You could use Pythagorean theorem to get its magnitude and the tangent function to get the direction if needed. And the point of this video is really how to get this thing rolling and how to analyze it. That's it. You know, the big ones, get the free body right. Make sure you define your system. Make sure you put the appropriate gravitational force vectors in. Then you're looking for contacts. This system has physical contact here and here. So you need force vectors here and here to take those into account. And again, whether you include the lamb in the picture, that's, in this example, that's up to you. If we didn't include the lamb, and we had a force vector down equal to tension 1 and no lamb, you would get exactly the same result, right? So really the only difference is whether or not this force is an mg for the lamb, and the tension T1 is internal and doesn't show up in the free body, or you have tension 1 here down equal to the weight of the lamb. Right? That's the only difference. The problem will work out identical either way. So I hope that this helps. Again, focus on drawing the good free bodies, then be very methodical about writing your torque equations. And then the rest should just fall apart after that, most problems that you look at. So hope that this helps. Have a great day.